All right, welcome everyone to our lecture on atoms with the subtitle "The History of Discovery." So we're going to talk a little bit about how atoms were discovered, what they are comprised of, and the scientists that made these discoveries. Okay, so John Dalton was the first person to come up with a theory to describe atoms. It's called John Dalton's atomic theory, and it has a couple of basic tenets. The first of these is that matter is made up of atoms, and an atom is the smallest indivisible part of matter. At that point, and when John Dalton was developing his theory, we didn't realize that there was anything smaller than an atom. Of course, we know now that atoms are made up of smaller things, but at the time, he didn't. Another tenet of John Dalton's atomic theory is that atoms of the same element are identical. So that means every single atom of copper is identical to every single other atom of copper. Again, we now know that this is not necessarily true because there are isotopes which have differing numbers of neutrons but the same number of protons, and so they aren't exactly identical to one another, but they're still, for example, copper atoms. We'll talk more about isotopes in a bit. Atoms can physically or chemically mix in whole number ratios to make compounds. So the way you make a compound is to mix a little bit of one atom and a little bit of another atom together, and you get some new compound. A compound is something that's made up of different elements. The important piece here is this whole number ratios part. So you can't have part of an atom. You can't have 1.5 hydrogens and 1 oxygen or something like that. You have to have whole numbers of atoms to make compounds. And this tenet of John Dalton's atomic theory still holds. And finally, the last one is that chemical reactions occur when atoms combine, or when they separate, or when they rearrange. So the definition of a chemical reaction is the separation, rearrangement, or combination of atoms. You don't get to make new atoms or destroy old atoms or whatever. They're neither created nor destroyed, but they're simply rearranged. That was one of the tenets of John Dalton's theory. Now, of course, we now know that you can destroy atoms, or you can take them apart into their smaller pieces, but we'll get to that. Here are some interesting facts about atoms, as we should know by now, since you took physical science in middle school. You should know that the atom is made up of a proton, a neutron, and electrons. Those are the three subatomic particles. The atom is the smallest unit of matter that has the properties of the element we're discussing. So you can't take a copper atom and take it apart into its protons and neutrons and still have copper. At that point, all you have are protons and neutrons. Atoms are really, really, really small. For example, something like 3 times 10 to the 11th meters, or about 3 picometers, really 0.3 picometers, really, really small. So small that a teaspoonful of water has about 3 times as many atoms as the entire Atlantic Ocean has teaspoons of water. So that might help you kind of get a grip on just exactly how tiny these things are. Over the course of the past couple hundred years, there have been a few different models that were developed to explain how the atom is built, what the structure of the atom is. And we're going to look at 4 of those models here. The Thomson model, the Rutherford model, the Bohr model, and then the quantum mechanical model. All right, so let's walk through those now. The Thomson model is the first one, and it was actually the first one that was developed. And that's because he was the first person to discover electrons. He thought that the atom here, he visualized the atom as a ball of positive charge. And you can see that here represented by these pluses. And embedded or dispersed within that ball of positive charges were small, discrete negative charges, the electrons. All right. Now, this is referred to as the plum pudding model, which probably doesn't mean anything to anyone anymore because no one really knows what plum pudding is. But maybe a better, more current model reference might be like raisin bread, where or a blueberry scone, where there's a bread or a batter of some kind, and there are these discrete little elements, raisins or blueberries or electrons that are scattered throughout it. So that's why it was called the plum pudding model. Rutherford was the guy that is the name of the guy whose model we'll look at next. He was the person who realized that atoms had a nucleus. In other words, that much of the atom was empty space. There's a small dense, positively charged nucleus in the middle of the atom, and then the electrons are outside the nucleus. So the Rutherford model was the first one that realized the electrons were not embedded in one big homogeneous blob of an atom, but were in fact separate from the nucleus. The Bohr model is the one that gets closer to what we have today, and in fact sometimes you'll hear people still use the Bohr model to describe how atoms are comprised, or what the structure of an atom is. Bohr proposed that electrons move or spin around the nucleus in orbits, and in fact we even call the paths that electrons move in are called orbitals. We still refer to them as that. So he had electrons in orbits, as you can see here, going around the nucleus of the atom, and for this reason it's referred to as the planetary model. Now it's not the most accurate, but we still will use that. It'll still come up as a reference point for discussing the structure of an atom at some point. You'll hear that. The current model, though, is called the quantum mechanical model. And it was developed by this guy named Schrodinger in like the 20s and the 30s, so quite a long time ago now at this point. And in this situation, the model of the atom is, well, at this point, we already know what the structure of the nucleus is basically unchanged. We know that it's a small, dense, positively charged mass in the center of the atom. What we're worrying about at this point is where are the electrons. The quantum mechanical model has the electrons not in orbits, nice, tidy orbits that spin around the nucleus, but instead the location of an electron is described by a mathematical equation that tells you how likely you are to find the electron in a given spot with a certain probability of being accurate. So the electrons have a probability region where you can find them, and that's what we're trying to represent with this picture here. As imagine this as a three-dimensional picture, not two-dimensional. So there's a sphere, and around this sphere is a certain probability region where you will find a given electron with a certain percentage of probability, 90% probability of finding an electron in a given space. That's how the quantum mechanical model describes the structure of the atom. Okay, we're going to talk a little bit now about how these different components, subatomic particles, were discovered. Let's start with the electron. It was discovered by Thomson, the guy who gave us the Thomson model of the atom, in 1897. And he used this device here, which is called a cathode ray tube. And so this is a glass tube, and there are wires that come out of the glass tube and attach to a power source, which is here. And inside the glass tube is there's one plate, one metal disc here, and one metal disc here, connected to these wires, and there's nothing between them, even though in this picture it looks like there is something between them. In fact, there's empty space everywhere else inside this cylinder except for the plate and the metal and the wires. Okay, so what we are representing by this kind of pinkish colored rectangle is a ray of electrons, we now know they're called electrons, that are moving from the negative towards the positive, positively charged plates. Of course, when you apply a voltage to this system, there will be one of the cathodes will be a negatively charged plate, and one of the discs will become a positively charged plate, and the electrons will move from the negative to the positive. Let's see what else we have text-wise. Yes, so here's our cathode ray tube. It's a tube filled with gas at very low pressure, or even a vacuum. You can see this part here where it leads to the vacuum pump. So this is basically evacuated glass tube. All right, and then there are two metal plates inside connected by electricity. So if you modify that setup just a little bit and put another disc right here that isn't connected to the electricity, but instead has a tiny slit right in the center, you can get a thin beam of electrons that move from this negative side towards this positive side of the cathode ray tube. Like I said, he realized, Thomson was going to realize that this beam was what was carrying the electrical current. If you then have this set up here and then you add a positively charged plate, so some kind of additional electrical circuit will be used here to make a positive and negatively charged plate here. Thomson showed that this stream or this beam of electrons that's moving from the negative towards the positive will actually bend towards the positively charged plate if you bring this close enough to the glass tube. So that told him that whatever was traveling from this side to this side was negatively charged because it was attracted to this positive plate. So he realized that whatever this was, whatever substance or compound or a subatomic particle was moving from here to here, it must be negatively charged. And that's how he discovered the electron. Let's talk really quickly about protons. So we know that atoms have no net charge. So atoms are neutral. The positive charges and negative charges in them balance out. So there's no net charge. We also know that electrical charges are carried by some kind of particle. They're not rays or beams. Their electrical charges are in fact some kind of particle. And we also know that electric charges exist as whole numbers. You can't have half of a charge. Okay, so knowing these kinds of things, and based on what Thomson told us about electrons, people realized that there must be something that represented the positively charged entity in this in the atomic structure, and in fact, there must be the same number of positive particles as there were negative, because the atom is neutral. So using our friendly device, the cathode ray tube, this guy named Goldstein realized that some kind of ray or some kind of particle was moving in the opposite direction from what the electrons were doing that had been demonstrated by Thomson. He called these oppositely moving particles canal rays, and I have no idea where canal comes from, whatever. But these things move from the positive toward the negative, so the opposite of what the electrons were doing. He decided to call them protons, or this is in fact what the proton is, and so Goldstein is credited with discovering the existence of protons. There is another subatomic particle, the neutron, and it was discovered by this guy, James Chadwick. And neutrons are neutral. They do not have a charge. They have zero charge, but they do have mass. And in fact, the proton has the same mass, the neutron has the same mass as the protons. The numbers of neutrons that you find in a given atom can change. So if you have, for example, if you have 6 protons in an atom, it must be carbon. If you change the number of protons, then you change the identity of the element. 6, if you add a proton to carbon, it's now nitrogen, 7. All right, so anything that has 7 protons must be nitrogen. Anything that has 6 protons must be carbon. That's not true with the neutrons. So you can have different numbers of neutrons in an atom, and that makes them different isotopes, but they're still isotopes of the same element. All right, and I think I have an example. So here's carbon with 6 protons. The most common isotope of carbon has 6 neutrons, and we call that carbon-12. If you add the number of protons plus the number of neutrons, you get the atomic mass. That's the 12. We call that carbon-12. But if you find, or if you create an isotope of carbon that has 8 neutrons instead of 6 neutrons, it's heavier. It's carbon-14. It has an atomic mass of 14, not 12, because it has 8 neutrons, not 6. Now remember, you can't change the number of protons because then it won't be carbon anymore. It'll be something else. Most of the elements on the periodic table exist in a variety of different isotopes. You can kind of I think of isotopes as flavors. There's a strawberry flavor and a chocolate flavor and a vanilla flavor because, I love ice cream and my references always come back to food. So I kind of think of isotopes as different flavors. It's all ice cream, but there are different flavors of it. Well, here we have different flavors of carbon, but it's still carbon. All right, so I mentioned earlier that this guy Rutherford discovered the nucleus, realized that atoms had a nucleus, a small, positively charged, dense component in the center of the atom. Here's how he figured that out, because that's kind of important. And in fact, this seems to be one of the favorite questions for them to put on the CSTs. For some reason, they like to ask about Rutherford's experiment, so pay attention. Rutherford was a student of Thomson, the guy who discovered the electron, um, and he used this device to discover, to study the structure of the atom. What we have here is a screen. So there's this rounded semicircular screen, um, and on the inside surface of the screen is a glowing fluorescent compound that glows when you hit it. And we have to stop.